All right, so welcome to another lecture of probability statistics. Now is the new year, so happy new year. Um, so this will be lecture number 11. So this plus two more, and then there's gonna be a lecture on how the exams will look like in life. And but today we will cover two, let's say, common tests that you will encounter if you go through statistics for your work. And one is the Komarov-Smirnov test, and the other is the famous Anova, or analysis of variance. And we will go through it, and we'll give you some examples as always to for a better understanding. So let's start. So for what is good, Komarov-Smirnov is the same idea or the same test than the chi-square test. So we try to see, or we would like to have a comparison between two samples, or between a sample and a given distribution. And we want to see if these two samples come from the same distribution, or if one sample comes from a theoretical distribution. So for example, here, the blue one will be our theoretical distribution, and the S here, the black one, will be our empirical distribution. So we made by our own data, and then the idea will be to see, to compare them. So how we can compare? Well, one way to do this is to see how far each point of the distribution is from the theoretical distribution. And Komarov and Smirnov came with an idea that one thing that is particularly very interesting is the maximum difference between our theoretical distribution and our empirical distribution. And this maximal difference will follow some kind of distribution, and then we can see if they are statistically different between them. So basically, the idea here is to directly compare empirical with the theoretical distribution and see what is the maximum difference, and then go and check if this is really significant or not the difference. So, like I say, this has the same function as the chi-square test, and so then why would you use KS test instead of chi-square test? Well, one limitation that we saw last time was that you really need to have discrete classes, and each classes will have at least to have 5 points inside. So at least you will have to have, if you have 5 classes, for example, has 25 values. And then sometimes real data is not that, it's some kind of scarce. So you might need to come up with another test that it doesn't require so many data. Some people say that Komarov-Smirnov test is more powerful than the chi-square test, but this is not really still, let's say, in debate. And like this test, there is other tests that we're not going to cover this lecture or this course, but are also very well known, like the Shapiro-Wilk test and the Anderson-Darling test, which Shapiro-Wilk test is usually or commonly used for testing for normality of the data, and the Anderson-Darling test have the extra favor that they not only you can say if the empirical distribution is following a normal distribution, but you can also estimate the parameter of the distribution. So, but just saying this, some people like more Shapiro, some people like more KS. In my experience, KS is usually less conservative. Shapiro is more conservative. So usually you will get, if your data is, let's say, not so close to the normality, KS will tend to say that it's more normal, and Shapiro will tend to say that it's non-normal. But this is from my experience. It's not that it can be generalized to all the cases. But for you to know, so chi-square test, we saw it. KS test, we will see it today. And but you know that there is at least 2 more tests to test for distribution. So you should explore all of them. So saying that, we'll make a small break. So I check corona regulations. Thank you. Oops. Ah, perfect. All right, so thank you so much. So now we come back. To our slides. So we have now another test. So the Komarov-Smirnov test. So like we say, so the difference that we saw here, it could be that the theoretical is larger than the empirical, the maximum is t, that the theoretical is lower than the empirical, so it will be minus t, or you can just check if there's different. You don't care if it's larger or smaller, the difference. So this will be the 3 cases. So you will try to find this maximum distance between the empirical and the theoretical distribution. And in the case that you are on the two sides, so you will have the absolute value of the difference. In the case that you are looking for the t that is positive, then you subtract the theoretical to the empirical. And if it's and the other way around, you subtract the empirical to the theoretical. Just this will depend on what you want to know. So this different t, like I say, it will change, right? It will vary depending on your data. And this variation will follow a distribution. And this distribution is given by this formula here. I'm not going to go to the proof of this distribution. It's quite empirical, but there is some kind of combinations and important key values here, but in general it's a distribution that will be tabulated, so you can look at values of the distribution depending on your t, on the difference. So again, you will have to set up hypotheses, as we always do, and the hypothesis will depend on what you want to test. But if you want to test that it's just that the theoretical and the empirical distribution is equal, you just is a two-side test, so you say that it's equal or it's different. Or then you can test that this is the empirical is larger than the theoretical, or the theoretical is larger than the empirical. This is up to you. So you can also, since we have the distribution, you can calculate also your p-value, right? So the value of the distribution, that will depend on your t that you calculate, right? And then by multiplying this, you will get your one-tailed p-value. It is, if it's two-tailed, like in the case that you only want to know if it's different, then you have to multiply this by 2, because you have the two-tailed, right? So it's symmetrical, so the p-value should be the sum of the two parts of the distribution. But we'll go through this, no worries. So examples always to make it clear. So let's say that we have collected 10 points, and 10 points are here, right? And now we want you to see if this empirical data that we have collected follows a uniform distribution that have the shape of the blue line here. So it's a invented distribution, and below 0 is 0, after 1 is 1, and in between is a linear relationship of slope 1 between x and the probability of x, right? And then we want you to see if our data here that we have follow this distribution. So we're just interested in if they are equal or if they are different. So it's going to be a two-side test, right? So how we do it? So we have to calculate, depending on our data. I don't know how the data looks, to be honest, but we'll have something like that. And then we have to calculate the difference, right, between the empirical and the theoretical distribution. So first of all, you will have to rank your data from the smaller to the larger, right? So you take your data and you calculate from x smaller to from f, sorry, smaller to f larger, right? And then you will have to some way discretize your distribution empirically, right? Since this is a linear relationship and we have 10 points, we can divide the whole spectrum of 0 to 1 in bins of 0.1, right? Then you have 10 points of 0.1. So the empirical should be something like this, right? 5, 7, 8, 9, 1, right? And then you will have to make a difference between them. If you calculate the difference, it will be, it's the absolute value, so we don't care how we subtract it, so 0.203 minus 0.1 is 0.1.03. 0.329 minus 0.2 is 0.129, right? So if you do the math, then you look at which of these is the larger deviance, and then you will have that this is the value. So this will become then our t statistics, right? The t that we are looking at. Now we have to find in the distribution of the KS test, which is the critical value that you are comparing to, right? Remember that after that you will reject the null hypothesis. So the null hypothesis in this case is that they are equal. Let's say that we pick 95%, that we want to have an error of 5%. Then you will have to enter a table, as always, of this distribution. And it will require the number of samples that you have, or the points that you have, and your alpha, right? Or 1 minus alpha. That table exists, as always, and then it will be tabulated in some way like this. On one side, you will have the number of points that you have. On the other side, you will have your alpha. So we say 10 point, and we say 0.05 because it's 1 minus 95%, right? Then you go to here, and this is something like 0.409, and this is what we have here, right? So now you have all that you need for see if your distribution is different from this theoretical one. Then this will be like doing this. So I draw it before, but this is our values. This is the theoretical. The maximum was 0.29, and our critical value is 0.49. So we are actually below this critical value. So I don't know, to be honest, how the distribution look like, but let's say that looks something like this. This is 0.409. To the left, you don't reject the null hypothesis. To the right, you reject it. We are to the left, so the null hypothesis is accepted, and we can say that at least by this test, the distribution that we have and the theoretical one does not, they don't, oh, they are equal. Okay, so the same way we can also calculate the p-value, right, of the distribution. So what will be the value actually here? And this way we use the distribution, remember, that we said just a few minutes ago, but we multiply by 2. Here is the 2, because it's a 2-state test. And if you calculate this, the p-value will be 0.307, which is much larger than 0.05, right, that we have set it. So it's really, truly not different. Yes, so that will be an example of a two-side test. If you have to go to one-side test, then this critical value, sorry, if you have to go to two samples, so this will be the case of having one distribution that is empirical against a theoretical one, but Komolov-Smirnov test is also can compare two distributions if they are different or not, right? So that will be a two-sample test, and in that case, you will have to have two samples, of course, that will have, one sample will have n point, and the other sample will have n point. It doesn't have to be equal. But let's say that we have, in this case, we have two distributions like this that actually have 10 points, both. So we can have 10. And then you come here and you say 0.05, 10 point, 10 point, and you get your table value. The table value will be 70. Okay? You plug it here, and you get your t statistic again. All right. So that's simple, uniform distribution. You can, like I say, compare to any distribution. So let's do another example with one sample test against the normal distribution. So let's say that we want to see if our data follow a standard normal distribution. How we do this? So again, we collect data. In this time, we have 8 points. And if we want to compare to the normal distribution, now we need to know, because we don't have the values like here, you just know that it's a normal distribution. So the normal distribution will be characterized by the mu and the standard deviation, right? So you need to calculate that. So the first thing that you have to do is calculate from your data what is your mu and standard deviation, right? And you will have to take these values and standardize them, because you want to know if this data follow a standardized and normal distribution. So for standardizing, you use your calculated mean and standard deviation. And then you start to do the same. So you have 8 points, right? Each point have a value, which you take from your data. And everything sum up to 90.8. Then you need to do the cumulative of this, because since you have a normal distribution, remember that the distribution is something like this, right? The cumulative density distribution. And then your data will be something like this, right? So you want to see if they are different. So what you do is start to accumulate and to create this curve. It's not like this. This is really bad. But if this is the real data, the real normal distribution, your distribution will be something like, I don't know, like that, for example. You accumulate, and then you have to find the maximum difference here, right? So you start to accumulate. So the first value is 9.8. The second value will be this plus this, so 19.9. The third value will be this plus this, so 30.2, so on, until you, of course, end up with 90.8, which is the sum of all, right? So the first value here will be 9.8. Oh, sorry. Okay, let me see if I can, how I can, yeah. Because if not, it gets really bad. So if your distribution is whatever it is, the first value here will be 9.8, and the final value will be 90.8, right? So now you have your values. Now you have to calculate the area under these values. So to calculate the area, you get all this divided by your maximum value. Okay, so it's kind of normalizing that, right? So 9.8 divided by 90.8 is 0.108. 19.9 divided by 90.8, it gives you 0.219, and so on and so forth. All right? So that is for our, and to here is our empirical part. Now we go to our standardized and normal distribution. How we do this? So we will have a value, and we have to see how this actually look in the real distribution, in our standardized distribution. So how we do this? We have to go to the table. It's quite tedious. So we go here, and you have to find so we go for, exactly, so we go for the, so for first, I forgot one point. So 9.8, you standardize that point, and it give you minus 0.55, right? So 9.8 minus the mean divided by the standard deviation give you the value of the theoretical standard deviation, standard normal distribution. With that value, you go to your table, and that is minus 0.659. So will be something in here, right? And let's say that we are we assume a 0.05. So it should be something like around here. And what we put here was 0.255. So it's kind of the average between them. All right? So then you repeat for the other. You take this value, you standardize it, and then you come and you get your set, and then you go to the table again, and you pick your area. With that, now you have everything you need. You have the theoretical part, and you have your empirical part, and what you do, you take the subtraction between them, and this is so 0.255 minus 0.18 give you 0.147. And again, this one minus this one give you this one. This one minus this one give you this one, and so on and so forth. And finally, once you have the car, you look at which one is the larger difference, and the larger difference is this. So 0.289. So far, so good. So this is our T statistics, right? So what we actually did was this. So this is our empirical distribution. This is the standard normal distribution. And this will be the limit depending on where we actually look at 95% and whatever. So if we exceed that limit, then they are not different. They are different. If you are inside these confidence intervals, you are good in saying that they are equal. So let's say that, so we have calculated this as a T. This is our T. Now we want it to be 95%, sure, so 5% error, alpha error. We have n equal to 8, 95%. We go to our table, 8, 95. We go to our table here, 8, 95 is about this value. I don't want to get exactly. So 0.454. 0.554. Okay? So that's how you get this value here. You look at the table, n equal to 8, 95. So now, again, so since the critical value, whatever distribution is, 0.454, so and this is less than this, then we can say actually that the distribution follow a normal standard deviation, standard normal distribution. I have a standard deviation in my mind for some reason. So we are to the left for this. Okay? Easy. I think it's simple. If I ask you in the exam, I think you will be really good at this test. All right. So summing up, KS is another way of comparing distributions, and C is a non-parametric method. As you can see it, it's about ranks. So they have nothing to do with parametric or parameterized methods. It is similar to chi-square, but for low n, it could be a good alternative. There are debates if they are better or not. And like I say, there are other tests that you should look at it that we're not going to cover in this lecture. All right, so up to here, we have finished, let's say, one part of classic statistics, which is looking at distributions, looking if a distribution follows some kind of parameters, and we look at if the distribution is actually looking as a distribution or not. So we have been done so far is usually we have, let's say, 2 distributions or 2 samples, and each of them will have a mean. If it is normal, let's say that they are normal, and both of them will have some standard deviation, right? And what we did so far is to see how these distributions are far apart, and how this variance is such that if they don't touch each other, usually they are different, right? And if the means, the difference between the mean 1 and the mean 2 are bigger, then usually you say they are apart, right? So far we have been doing pretty much that. What we're going to enter now is a multivariate analysis, so more than 2 samples, so we'll have another sample here. So if we have at least one another, it can be more than one more. So we will have a mu 3, and we will have a standard deviation 3, if we're talking about normal distributions, right? And now we want to see is they are different. So one alternative will be that you look at first 1 and 2, then 1 and 3, and then 2 and 3. You could compare them. And then whatever is different is different. The problem is every time you do this comparison, you are committing an error that we know that is at least 5% if you like to have an alpha of 9%. So you will be inflating this error every time you do the comparison. So there is better way to do this is to put everything together in one framework, and this is what you call the multivariate analysis. So there are basically 2 types of technique. You can divide this. One is if you look at variables that depend on other variables, and if you like to look at independence between the variables. We will be covering left, and we will be covering only when you have one dependent variable. So there is one measurement, and you want to see if some variable affect this measurement. You could have 2 or 3 measurements and see how this variable affect, and then you will be here, right? And the most common, if your data follow a normal distribution, is using the analysis of variance, right, or covariance. Analysis of variance is what is called Anova. This is the password of your Ilias website. Analysis of covariance, you look at the instead of look at the variance, you're looking at the covariance. But we're not going to cover Anova, which is called Anova. If you will have more than one dependent variable, then you will come to, for example, Manova, multivariate analysis of variance. Then you will have many measurements and many factors, and you will try to analyze that. So what we're going to focus today is with this, which is analysis of variance. And before even we go there, I want you to see how this is done from the concept. So let's say that you have these 3 distributions that I have here. So how you can tell that they are different? That they are different, not that one is different to the other, that some of them are different. How you can tell that? Well, first, if the variability inside of each distribution is small, then probably they will not touch each other, or there is more chances of not being touching each other. And if the variability between them, so the whole variability is large, probably they are separated apart, right? So that's pretty much the concept on Anova, is to see if the variability inside of each sample is much smaller than the total variability that you will have, okay? And that will be the measurement of how spread they are. Of course, with that, you cannot tell which one is different to the other. You can only tell that they are separated apart. Then you will have to run another test to see which one actually are separated. So saying that, we can start. So Anova, of course, that's what is called analysis of the variance. You don't care about the mean, or you care, but you care more about the variability. That's what it's called about analysis of variance. It's, of course, a parametric method, and imply that the data or the residual to your model is normally distributed. If not, you cannot use it, or it lose power, let's say. And basically, this is what I said before. Basically, you have independent and independent factor. The dependent factor will be the thing that you are measuring in 3 different cases, for example, in our case. And independent factor is which factor is the factor that is influencing this measurement. And this is what you want to see. So, for example, in the case of here, let's say that we are measuring temperature with 3 different temperature thermometers, right? So the dependent variable will be the temperature, and the independent factor will be the thermometer. And in this case, for example, we have 3 thermometers. So our dependent variable will be temperature, our independent variable will be thermometer, okay? Then you could add another factor, for example, and say, well, the temperature is measured depending on the thermometer and depending on the room temperature. Then you will have two factors influencing the temperature, the room temperature and the thermometer, okay? So, and you can add more factors if you want. But for now, we're gonna keep simple, and we're gonna go in the case that we have only one dependent factor and only one independent factor and one dependent factor. And this is called single factor analysis or one-way ANOVA. When you have two factors that are independent, you will call it two-way ANOVA or dual factor analysis. All right? Good. So let's start with the example to make it think clear. This example will be about single factor analysis. So we start from there. So congratulations, you have promoted from being measuring nails to screws, and now you are doing quality management. So you are now a full engineer in the production, and you have 3 lines of productions. And they are doing some kind of pharmaceutical agent. So COVID pill for cure COVID. And these 3 in production are independent, so they are run independently, and they're supposed to work equally. So they will produce the same kind of pill or with the same property that you would like to have. And this is by measuring this pharmaceutical agent, is that you are clear that they are doing well, the 3 of them. If not, it will be your job to find out which one is not working and then go and fix it, right? That's the idea of this example. So they're supposed to work identically. They're supposed to have the same path. And there's no distortion here that we're going to consider. And of course, they will have the data distributed normally. And we will take 5 samples of each production line. So we'll have 5 points from each of the 3 lines. And we want you to see if they work equally. So we collected data, and we have then our 3 production lines. And each of them will have some value of the agent, whatever that means. I don't know. Amount of chemically, I don't know. I don't know anything about chemistry, but I cannot say anything. Some chemical measurement here. So we have 5 times 3 production line, 15 points. And then we say that we have to look at the variability inside and the total variability, right, for all the values. So to make it, to find the total variability, you have to first find the mean, the general mean, right? And then how these points are different from the general mean. So if this is a plot, there has to be some kind of general mean here, big mu x, and the points will be different to this mean, right? And you also have to find the dispersion in general, and then you will have to find individual means and the dispersion to the individual means, and that will be the within variability, right? Or we can call it within variability within the sample, between variability the whole sample. So that's what we do here. So we calculate the mean for each production line. So that will be like mu1, 2, and 3, and the standard deviation from this point. But we also calculate the general mean, so the mean of the means, and the general standard deviation we could calculate, right? So far so good, right? So we are clear that the independent factor is the amount of agent that we have here, and the independent factor is the production line, right? So this is what I was saying here. So within a group, overall group is the mean that we have to calculate. So once we have this mean, and we have the point, and we have each of the means inside, so we have the means for each of the distributions, and we have the large mean, then we can look at the deviations between them, right? It's the same by looking at here. You have your big mean, and they look how each of the means deviate from this big mean, and how each of these points deviate within so how the points are deviating for each of the mean, and how the means are deviated from this big mean. All right, so we look at the variability within the sample and the variability of the whole between group samples. And how will we do this? So we have to find some kind of measurement of the variability. And what we do is we calculate the variance. It's the best way because it's follow a normal distribution. So how we calculate the variance? Well, first we have to calculate the sum of the squares. And they're going to be some sum of the square of the whole thing, so between samples, and the other has to be a sum of the square of the within. So the sum of the square for each class or each sample, and the sum of the square for the total population, or the total group of data. And if you sum the sum of the square between plus the sum of the square of the within, will give you the sum of square total, right? That's one part. So how you calculate this sum of square? Here is when it starts to be elaborated, and if there is something like this in the exam, I will try to make it simple for you, but maybe this happens. So to calculate the sum of square within, you will have to subtract each point of your sample. Here I and J are indexing production line and samples, right? So you will have to take each of the samples within the each of the points within the sample and subtract it to the mean of that sample. So we are talking about you have the sample, you have the mean or the average, and then you have each point, there is a deviation from that, right? And then sum it together. It's like when we do, remember the variance is 1 over n or n minus 1, summation of x minus the mean square, sum of the square. So this is the variance. So we are doing the same here, but for this case. So what we're doing is here is we are doing this variance for each of the samples, for the 3 samples, and sum it together, okay? So we start with, for example, sum of within. Within we are here. So our points are 43, 40, 41, 60 something, 63, 66 for 2, 52, 50 for 3. Our average was calculated as, for the production line, for example, 1, was 41.6, right? So if you subtract 41.6 to 43, right, you make it square, you get it here. And then if you sum it all together, this is your value for the first production line. Then you will have the same for the second production line and the third for the third production line. Then you sum it together, and this is your sum of square within 42. Then you have to go to the between. The between you have to make the mean of your sample minus the general mean and square it. And you have only one summation here because you don't have, the mean is always, there are 3 means only, right? So you come here and you have to repeat your mean, right, many times, and you have to subtract it to the general mean, which in our case was, general mean was 64. So if you subtract and square, it gives you 121, repeated many times, 605. For the second production line, 649.8, and for the last production line, 0.8. So if we sum together, it gives you 1,255.6 for the sum of the square between. So you already can see the variability within the sample is 42, and the variability between the samples is 1,100. So you can already guess that this is look like they're far away apart, but we still don't know. And then you will have the total, which is this plus this, it gives you the total, right? Or you could do the formula by each point minus the grand mean, square it, sum it together for all, and it will end up with the same number. But I will just sum up these two. We actually don't use it, but it's for you to know. So, but now we have the sum of square, but it's not, if we will finish here, the result of your test will depend on the number of samples that you have, because the more samples you have, the difference will change. So we have to kind of standardize. And this is what we do with the variance. So we have to do the same. We could do like the variance, that we take the sum of the square and divide it by n minus 1. But then we will have the problem that also depends on n. So what we have to depend is on the degree of freedom. And we come back to our concept of the degree of freedom. And what we do is we take each of the sum of square and we divide it by the degree of freedom, which will depend on the number of the production line, on the dependent factor, and also on the data. So for each of these sum square, they're going to be defined degree of freedom. So for example, for the total degree of freedom will be the number of production lines times the number of points minus 1, and that will be 3.5 minus 1, 14. The degree of freedom for the between will only consider the between factor, so we have only 3 production lines, and we subtract 1, it gives you 2. And for the degree of freedom within, we will consider, again, 3 production lines, and we will multiply it by the number of points minus 1 each time we do this. And that gives you a degree of freedom of 12. So now we have the degree of freedom for each of them, then we will be able to calculate this variability, the variance, the true variance. So we will take each of these values that we get here, and we divide it by the degree of freedom. And that's what we do. So the total variance will be the sum of square total minus the number of degree of freedom. It gives us 92.69. The total the variance of between is the sum square between divided by the degree of freedom, 627, and the degree of the variance of the sum square within is the sum of square within divided by the degree of freedom, 3.5. Okay, so now you can see, now it's scaled to our problem. We came from 42 and 1,255 to 3.5 to 327. So still, it looks like the variability within is much smaller than the variability between. So how we can actually see if they are really statistically different? Well, there's going to be a distribution for this. Okay, so the ratio between the ratio between the variance between dividing the variance within is what is usually called as the F value. You will find it out, right? This is our statistics, right? And this F value, it will follow some distribution. And before I go here, this distribution is defined by the F distribution, which was actually invented or developed by Snedeker, but he was a big fan of Fisher, so he called it Fisher distribution. And that's why we usually call it the F value. And the idea is that since you have a ratio, and it's a normal distribution, sum it together, sum of square, you have a chi-square distribution divided another chi-square distribution. And that's how you create this new distribution that you will look like. Okay? So the chi-square in the numerator will be for the between, and in the denominator will be for the within. And no worries about the distribution itself. It looks something like this. We don't care here. We are not going to the statistics or the mathematics of this, but I want you to see where this comes from. And this distribution, of course, will be tabulated. So it will look something like this. And then you will have your critical value, and to the right will be rejecting the hypothesis, to the left, you will be accepting the null hypothesis as always. But I just jumped this because this is another way of looking at the ANOVA. And if you have noticed it, and sometimes it's difficult to graph this, but this difference between the samples is nothing like doing a regression analysis, right? Where you want to estimate your values with some grand mean, some difference between the grand means and the each mean of the samples and the grand mean, and some error that you will have, right? And you want to see if this regression is significant. If the slope of this regression is significant, so it's actually a correlation, then it means that your dependent factor is correlated to your independent factor. And it means if this is correlation, it means that they affect actually your measurement. Okay, this is another way to think about the ANOVA and any linear mixed model or any model that you use with a linear regression between them. So this is important too, because what we are modeling here is a linear regression or linear dependence between them. If they have a nonlinear dependence, then it will be different, the analysis that you have to say. So not only you will say that if we find it significant that the production line affect the quality of the agent, but they affect linearly, okay? This is kind of important too. All right, so having this distribution, then we do the ratio between the between and the within the variance and give you the statistics. In this class, we call it PG, but sometimes you call it F. Usually when you report your result, you report the F value, which is the statistics, and then you will report the p-value associated with that, okay? So 179 is 179.37 is larger than our critical value. You reject the null hypothesis, and it's smaller. If it's smaller, you reject the null hypothesis. Sorry, if it's larger, you reject the null hypothesis. If it's smaller, you keep the null hypothesis. So this is what you say here. So how we calculate the critical value? Again, table. For this table of the ANOVA, there are two things or three things. First, you have to know the alpha. Then you need to know the degree of freedom of the between and the degree of freedom of the within. Fortunately, we have those of them. We have to set alpha. In this case, we set alpha to 0.025. And then will be a specific table for each alpha separately. And each table will look like this: degree of freedom of within in this direction and between in this direction. Okay, so you look at 2 and 12 from our data, and they give us 5.1. 5.1 is way smaller than our F value or PG value, and then we can reject the null hypothesis. What we are saying is that they are not equal. So the production line actually affect the quality of agent. We don't know which production line is actually affecting, but one of them is different. At least one of them is different to the other, to some of them. Then you will have to run with something like it's called post hoc analysis, which is not covered in this class, but it will be some kind of t-test, but it's not exactly a t-test. All right, but this is for more advanced lectures. Okay, so far, I hope so far so good, because now it gets a little bit more complicated. So now let's say that our production line, we only not want to test if the production line is affecting, if some kind of pH value in the sample or in the process will also affect. So now you have two independent factors and one dependent factor. The dependent factor continues to be this agent that you measure. The independent factor is now production line and pH. So the analysis, we'll see that it's pretty similar, but yeah, but we don't, it's a little bit more elaborate. So the first thing that when you have a two-factor analysis, and also for when you do t-test, is to see if they are related, this production line with the pH. So if the independent factors are related. If they are related, you have to do another analysis. If they are independent, then you can do what is called two-way ANOVA. If they are dependent, you will call it something like two-way ANOVA with repeated measurement, or mixed ANOVA sometimes, depending on how this works. But this is topic for another lecture. And so how we can see quickly if they are independent or not, this is a graphical way to see. You calculate the mean for each pH. So pH is now divided in acid and basic. And we have 3 production lines. So you calculate the mean for each of the pH and each of the production lines. So you will have at the end 6 means. And you see how these means actually varied. So here you have Asian measurement factor, and it's parameterized by pH. Okay? So you can see that as you move from one factor, one production line to the another one, it's going up from 1 to 2, and then it goes down to 2 to 3. And both pH look to follow the same, so probably they are not dependent. Okay? If there will be some kind of interaction between them, you will have something like crossing lines. Okay? So this is also a way to quickly see if there is pH and production line will interact each other. Okay? But in this case, it looks like they are parallel, so they look like they all. There's a strong influence look for factor 1, but factor 2, what is pH, is not looking too much change. But we will see. So we have our means. The first thing that we do. Now our model of the sum of square changed a little bit. Before we have it that the sum of square, always sum of square total is equal to sum of square between plus sum of square within, right? Now what it changed now is the between, because now we have 2 factors. So between we'll have the between factor 1 and between factor 2, and the interaction between them. Okay? So if we now add that to our equation of sum of square total, so it will be the sum of square between plus the within, which stay the same. So now our regression formula changed a little bit too, because we have the grand mean, we have the difference from factor 1 to the grand mean, the difference between factor 2 and the grand mean, the difference between each point and the grand mean, and the difference and the error, of course. So it gets a little bit more complicated, but still the same idea. It's a linear regression between them, or a linear association between them. So now we come to calculate our sum of square. And this is really tedious to do it by hand. Hopefully, and good that we exist software like R that give you a package and calculate for you. But this is what the program is doing. First, you have to calculate the sum of square total. You're not going to use it, but it's important to have it because you can do a shortcut. I will show you. If you do this, you have to take each value for each production line for each factor to the pH and for all the points, and subtract it to this grand mean, square it, and you see that you have now 3 summations. One is for the production lines, the other is for the acidic or the pH, and the third is for the points that you have in each of them. So that way you calculate the total sum of square. The sum of square between for factor 1 will be, as we did it before, the mean of each factor to the grand mean multiplied by the number of samples that you have inside. And the sum of square of factor 2 is the same, so but now the mean is for factor 2. And you again multiply by the number of samples that you have inside. If you do this with the data that we have here, you end up with these values. The sum of square total is 2,541. The sum of square for F1 is 2,444, and the sum square of F2 is 32.14. What you can already say is the variability between for factor 1 is much larger than for factor 2. Okay, so this is already telling you something. So final one is we have calculated this, we need the interaction between them. For the interaction will be each of the point minus the difference between the mean for factor 1, the mean for factor 2, and the big mean. You sum a square and you multiply by the number of points that you have. Again, these are examples of how you calculate this guy here or this guy here. So you take the mean of factor 1 plus the mean of the factor 2 minus the ground mean. It gives you the first mean asterisk that we call it, or mean of the interaction. And if you do that the same, then you sum all these guys together, they square it, and it gives you that the total sum square, or the sum square of the interaction is 0.47. Very small. The interaction, this is big, this is small, the interaction is even smaller. So probably there is no interaction. The variability is very small. So we sum it together and we get the between. So now you could go again and calculate your within, right? How you do this? You have to take each value and subtract the mean and sum it together. But you can do that, go ahead with that, but you can also do the formula that if you subtract from the total, the between, you will get the within, right? So you just shortcut it and you get 64.8. And that's why it's good to calculate the sum square of the total, even if you don't use it for the analysis. So now we have the sum square. What we need? We need a degree of freedom, right? Because we have to find the variance. Degree of freedom for two-factor analysis. First, degree of freedom of the total. Multiply the three number of samples that you have in each of the group. So we have 3 production line, 2 pH, 5 point inside of each, minus 1, 29 is the degree of freedom of the total. The degree of freedom factor 1 is we have 3 production line minus 1, 2. For factor 2 is we have 2 pH minus 1, 1. Degree of freedom of the interaction is the number of production line minus 1 times the number of pH minus 1. It gives you 2 times 1 is 2, sorry. And the within is the number of production line, the number of pH times the number of points inside of each group minus 1. It gives you 24. So now we have the degree of freedom for each of them. We calculate the variance finally. Total variance. Sum square total divided by degree of freedom total, 87. Variance of the sum square of factor 1, sum square factor 1 divided by the degree of freedom of factor 1. Variance of between sample of factor 2 is sum square factor 2 divided by the degree of freedom, 32. Variance of the interaction, sum square interaction divided by the degree of freedom of the interaction, 0.24. And finally, variance of the within, sum square within divided by the degree of freedom within, 2.7. So what you can see? You can see that the whole variance look like to be here for factor 1. So it looks like there is a well separation between production line, not so well separation between pH. It looks like the interaction will be not significant because it's very small, the variance, so they are very tight together. And the variance within is very small compared to the other variance. So probably there is very narrow samples and they are apart, far apart. But we have to test it. How you test it? You get now 3 PG or 3 S values. And one is for factor 1, 2 is for factor 2, and 3 is for the interaction between them. So the ratio for factor 1 will be the variance of factor 1 divided by the variance within, 452. For factor 2 is variance of factor 2 divided by the variance of within, 11.9. Interaction, variance on interaction divided by variance of the within, 0.09. You notice that we always use within, right? Because you always have to compare to the same value. So again, you can see that the values are quite different. Now we have to calculate our our critical point. And how we do this? Well, each of these PG will have degree of freedom, and we will always compare to some alpha. In this case, we again continue to 0.025. So we go to our table here. Degree of freedom numerator, denominator. For the case of the between factor 1, we have 2 for the numerator, 24 for the denominator. Factor 1 is, so you have 3 production lines, so you have 2 degrees of freedom, right? So factor 2, you have 2 pH, so 1 degree of freedom, 24 for the within. Between interaction, you have 2 and 24. So this is the same degree of freedom that we have seen before. And these are critical values. So everything above this critical value will be significant. So we will reject the null hypothesis. Let's check for each individual. Well, it looks like PG1 is much larger than the critical value for PG1. So what we say, factor 1 influence the agent, right? So the production line, again, is influencing how the agent is coming out. 11.9 is actually larger, not so larger, but it will be larger. So we actually say that also the pH is affecting the agent. If they are interacting, so they are interacting the two factors, well, 0.09 is much lower than our critical value, 432, so they are not interacting, so there is not significant. Of course, for each of these critical values, there will be a p-value associated, and this is usually what you report. Usually you report your F or PG, whatever you want to call it, and the p-value. That's how you report in the literature, or if you have to do a report for your boss, whatever. And that's it. So that's a two-way analysis of variance when you have, it's a parametric method when you have normal distributed data. And I think with this, we have finished. I hope you have a good overview. There are other methods that we're not going to cover here, like linear mixed model, like generalized linear mixed model, many others that are different for different class of data. But if you have a normal distributed data, Anova is the way to go. If it's not normal distributed, then you have to go to non-parametric methods or this other linear mixed model, which will help you. In general, generalized linear mixed model cover everything. This different with this method and Anova is that in the generalized linear mixed model, you can assign the distribution that you want to your data, and that makes it more flexible. But at the end, it will be doing the same. All right? Okay, so with that, thank you for being here in this cold weather and very early moment, and I see you, I guess, next week.